Hi there, guys. Welcome back. This is another Chem Complete episode for Organic 2. We're continuing the ketone and aldehyde lecture today, and we're going to take a look at the first of the major reactions for nucleophilic addition to a ketone or aldehyde, and that is going to be the cyanohydrin addition. So just one or two things I want to mention here. First of all, a lot of these reactions are going to be additions when we're dealing with aldehydes and ketones. So you're going to see addition here a lot, whereas we've seen a lot of substitutions previously. Cyanohydrin, the cyano group is a C triple bond N. And when we deal with hydrin, if you remember when we would do halohydrin additions to alkenes, which are double bonds, we would usually add a halogen and an OH. So what we're really resulting with here, the resulting product, is going to be a cyanohydrin or a nitrile and alcohol group that we are adding to the aldehyde or ketone. Now, before I get started, let me bring up the general reaction here, and I want to make a note. So I'm going to start doing this with an aldehyde. Very sterically hindered ketones tend to have trouble with this reaction. However, ketones that are not sterically hindered can readily undergo this reaction, and most aldehydes will undergo this reaction because the hydrogen is not sterically hindered whatsoever. But if you have like phenyl groups or other very large groups, it might be a little more problematic. This reaction, first of all, is in equilibrium. And so we show the back and forth arrows like this because this is a reversible reaction. And what we use is HCN. All right, now if you use just HCN, this reaction is very, very slow. And so we tend to add as a catalyst a little bit of minus CN in with the HCN. And that's fine because if this is, even though this is an acid and a base, the base here is the same as the conjugate base that would result from this acid being deprotonated. So you could pass the protons back and forth. You'll always have some conjugate or original minus CN in solution. And so that's not problematic. Adding this nitrile, the negatively charged one, will greatly increase the reactivity of this reaction and the rate of this reaction. So what we end with, and we'll take a look at the mechanism here in a second, what we end with would be the cyanohydrin, which is what we have over here. And one of the reasons we're really interested in the nitrile groups is that these can be converted into other functional groups, which we will take a look at in the second half of this video. So these can be converted into carboxylic acids. They can also be converted into amines. Both very valuable functional groups that we might be interested in. So, one of the other things I want to point out here, a lot of students will ask, okay, well, if I can add this, how come I can't do this reaction with something like HBr, which is, right, that gives H plus and Br minus, just like I would have for HCN, I would have H plus and Cn minus. So a lot of students think that basically if I pick out any acid that has some sort of a corresponding conjugate base that could act as a nucleophile, that this reaction will occur. And that's actually not the case. Cyanohydrins, or the nitrile addition, is almost really viewed as an exception because a lot of these other compounds are, when you look at the product in comparison to the stability of the starting material, it tends to favor the aldehyde or the ketone form when we're dealing with the equilibrium. It's pretty unfavorable when you look at the equilibrium constants for the Br addition over here on the right-hand side, or if you did HCl or even H2SO4 or H2O to try to get like a geminal diol, you're going to have issues where it pretty much always reverts back to the aldehyde or the ketone for the most part. But the cyanoadduct that we get over here, this is pretty stable, and so this is not a problem. It's certainly a reversible reaction, but it is not a huge problem in terms of getting this to proceed forward and not solely favor the aldehyde or the ketone form. So just wanted to sort of mention that. I'm going to delete those because we're going to open up here and talk about what we're working with. So if I have some catalytic amount of CN here, so this is what we're really dealing with when we have the minus CN. This is going to be considered a base catalyst, right? And one of the definitions when we deal with catalysts, you guys should be familiar with this from previous reactions, is that a catalyst is always returned to us at the end of a reaction. So we should get the nitrile anion back at the end of this reaction. So here's what's going to happen. You've got the CN minus, and I'll put a lone pair up here just so we can clearly look at how this is going to behave. So the nitrile itself is going to go after, keep in mind this would be partially positive, and we have partially negative for the oxygen here, right? So this is going to go after the partial positive. Now that carbon involved in the aldehyde, that carbonyl, that already has 4 bonds. So carbon can't have more than 4 bonds. So, and this is a very good warm-up, but you're always going to be seeing, anytime the carbonyls attack, this sort of behavior. The oxygen needs to accept some electrons from that carbon-oxygen double bond in order to make room for the incoming group. And so what we get is a tetrahedral intermediate state. So a lot of our intermediate states that we've seen have been sp2 hybridized. They only have 3 bonds and a carbocation. This is a tetrahedral intermediate state that we would have. So our intermediate here, and this is somewhat similar to a Grignard reaction, which we will cover again briefly, but we've already looked at that with the alcohols, right? So now I have the C triple bond N, the nitrile group that has attached itself, and up here I've got the O minus, and this would be my intermediate as far as this reaction goes. Now, keeping in mind that this is a catalyst, so I want to regenerate the CN minus, and I'm headed up in this direction. The next thing that would occur is that the HCN, which is an acid, will be deprotonated by the O minus that's there. So this is where the alcohol comes from at the end, right? And then I regenerate the CN minus. So that's going to produce CN minus so that I could restart this again if I wanted to. And I end up with my cyanohydrin as the product. Okay, so let's clean this up. That was an example of the mechanism. Let's clean this up and do a real clean mechanism with an example, an actual example of a compound, not just R, where we can see this at work, right? So let's say we'll do a ketone this time instead of an aldehyde. Got to keep this group somewhat small so that it's not too sterically hindered. A methyl is certainly still acceptable. And so what I'm working with here is HCN. Okay, don't forget there is technically an arrow going back this way, and CN minus. So these are what I need here, right? In fact, you know what? Because I don't want you guys to view that as just CN minus in the reverse way. So let's put comma CN minus like that. There we go. Okay, so the way this is going to work is that the nitrile, the catalytic base nitrile, is going to open up the carbonyl, and my tetrahedral intermediate that I would get, I would keep the ethyl. This would now be O minus with an extra set of electrons because it accepted from the double bond. The carbon in the carbonyl accepted the nitrile coming in, and then I've got a CH3 group here on the other side. And so the second step that would occur here, because I have the presence of HCN, is that one of these lone pairs on the oxygen would go after the hydrogen. This would regenerate CN minus, and so at the end of the reaction I would get the cyanohydrin that would look like this. And I would also get the nitrile anion back. So plus, right, I get my catalyst back, and I could use that to recycle and basically start this reaction over again. So that is the mechanism and the process, the synthetic process for the cyanohydrin addition. Now, just a point here, because I did say there were two other reactions. We're not going to get too overwhelmed with the mechanisms for these, but they are important to keep in mind. If I have, we'll go back to the aldehyde example. If I have an aldehyde and I choose to do a cyanohydrin addition, I end up with the cyanohydrin. Now, one of the things that I can do after I have this nitrile group, okay, and this is if I find another way to put a nitrile group on it. It's not exclusive to the cyanohydrin addition. However, that's one way that we could put a nitrile group onto a compound like this. I have two future reactions or alternatives that I can utilize as far as the nitrile group is concerned. So the first thing that I could do is I could reduce the nitrile. And to reduce the nitrile, I'm going to use a strong reagent. So I would use LAH, lithium aluminum hydride. You should be familiar with that from the alcohol chapter. And then I could follow it up with something like H2O. And what I would end up with is I'm going to, if I reduce this, I'm getting rid of these double bonds and adding hydrogens, I would end up with the corresponding amine. And so what I would create here would be CH2NH2. I'm adding hydrogens to the nitrile, and then I would still have my alcohol present up at the top. Now, if I wanted to if I wanted to rewrite this so it's a little bit cleaner, okay? If you take a look at this down here, what I have is R. That H coming off can just be written as CH. The amine could continue, so CH2, I'm sorry, not C, NH2, CH2NH2, right? And then I would still have my alcohol attached here. And so this would be the resulting compound of running through a reduction post addition of the nitrile. Now, the other thing that I could do, if I was interested, is I can really look at oxidizing this nitrile group. And you can simply do this with H3O plus and heat. That's the only thing you really need to utilize here. So with H3O plus and heat, I will get a carboxylic acid out of this. And so I'll do the same sort of thing here. I would have the OH, I would have the H, okay? And then I would have the COOH. And so if you wanted to sort of rewrite this so it was a little bit cleaner, you're dealing with RCH. There's an OH attached to that CH. And then over here I've got C double bond O, OH. Notice in the oxidation we are going to replace the nitrogen with oxygens as we do an oxidation. And so I get the carboxylic acid functional group in place of the nitrile group. So the nitrile in each case, one time you can still kind of see the presence of the CN in the amine. It's just got additional hydrogens in place of the pi electrons. And then when we do the oxidation over here using acid and heat, this guy, that carbon down there in the carbonyl is the same carbon found in the nitrile, but the nitrogen has been replaced with an OH group, and so we get the carboxylic acid. So those are two side reactions that you would want to be able to utilize or know about because they're very useful. So that about does it for the cyanohydrin addition, a very important reaction to start with, but certainly not the only one. So we will continue to take a look at some of our other reactions that we come across. And I do want to mention one more time, I probably will not include a separate video on this because we've already discussed it in the alcohol chapter, but if you're watching the playlist, I may include it again. The Grignard reagent. So Grignards and adding those to carbonyl groups will form alcohols. If you have any problems with that, go back and watch the old video in the alcohol chapter, the alcohol playlist, and you will be up to date in terms of our Grignard reactions. So I will see you guys for the next video where we will continue our aldehyde and ketone lectures. Please remember to like, comment, and subscribe. I'm happy to take questions in the comments section. Subscribing will be the quickest way for you to get updates whenever I post new content. Thank you for taking the time to learn with me today. I hope you guys have a wonderful rest of the day, and I will see you next time. Take care.